All right, let's jump straight into today's explainer. I'll be your lead structural engineer today, and listen, we are going to move way past just memorizing building codes. For all you construction site supervisors and engineering students tuning in, we're really going to dig into the unforgiving physics behind exactly where we place our rebar lap splices. Boom, the structure rips itself apart at the splices. Now, that is a dramatic statement from a structural engineer, but it perfectly captures the catastrophic stakes here. You can design a building to shake and shift. I mean, that's what it's supposed to do, right? But if you've got lap splices sitting in the wrong zone during a seismic event, boom, it literally rips itself apart. So here's the puzzle we need to solve today. Why does a perfectly good piece of tied steel suddenly become this fatal weak link the second the ground starts shaking? To really get that, we have to look under the hood at how reinforced concrete behaves under extreme stress. Here is our roadmap for the explainer. We'll start with the anatomy of failure, dive into the physics of plastic hinges, cover the golden rules for beams and columns, look at the staggering principle, and finish up with checking the drawings. Let's get to it. Section 1. Anatomy of failure. We're looking at elastic versus plastic deformation. Okay, the foundation of our entire lapping strategy really comes down to how deformation works. Under normal, everyday conditions, we're dealing with elastic deformation. A load hits, a crack opens up, the rebar stretches a little bit, load goes away, crack closes right back up. But during a severe earthquake, we actually want plastic deformation. We need it to safely dissipate all that massive seismic energy. In this state, the rebar yields, it stays stretched out, and that crack remains permanently open. But here is the massive danger. If you have a lap splice sitting directly across a crack that permanently opens, well, that bar is no longer fully developed. It entirely loses its capacity, and instead of safely yielding, it just suddenly snaps or pulls out. Section 2. The physics of plastic hinges, otherwise known as the danger zones. So where exactly does all this extreme plastic deformation happen? Enter the plastic hinge. These are the specific, calculated locations in our structural members where we actually allow inelastic rotations and severe damage to happen. Think of it as a sacrificial zone meant to absorb the earthquake's punch. Now imagine placing a splice right in the middle of a plastic hinge zone. The concrete crumbles away, just like it's designed to do, and suddenly, your steel's development stops dead in its tracks. If there's a huge open crack right at the halfway point of your splice, that steel simply cannot reach its yield limit. It's supposed to hit that limit and stretch, but instead, it violently rips out of the remaining concrete, and you're looking at total failure. Section 3. Golden rules for beams and columns. Let's talk about field application. All right, let's translate that physics into actual actionable rules for the field. How do we keep our columns and beams out of these danger zones? Let's start with columns. I want you to really think about this next time you're out on site. We lap in the middle of the column. Always. Why? Because during a lateral seismic load, the top and bottom zones of that column take the absolute highest bending moments. If you lap at those ends, you are creating massive stress concentrations right where a plastic hinge wants to form. The middle of the column is what we call the intermediate zone. It's got the least bending stress. Put your laps there, and you keep the joint under way less stress, ensuring the structure stays safe. Now, for beams, the ACI provisions lay out a brilliant, extremely specific rule. You have to intentionally push your splices completely away from the face of the supporting column. The code dictates a minimum distance of 2 times the depth of the beam. You'll often see this written as 2H, away from the joint face. Doing this guarantees your splice stays entirely out of that highly critical plastic hinge danger zone. We are purposefully placing the splice in a quiet region where those longitudinal bars are never expected to yield in tension. And hey, as a quick back-of-the-napkin rule of thumb for calculating the actual lap length out in the field, we generally use 50 times the diameter of the bar, or 50D. So if you're working with a 1-inch bar, you're looking at roughly a 50-inch lap. But obviously, please remember, that's just a baseline. The precise length is going to depend heavily on your specific bar grade and concrete strength. Section 4. The staggering principle. Let's avoid creating any weak links. Okay, so you found that perfect low-stress intermediate zone. Awesome. But there is another major trap you absolutely have to avoid, and that trap is congestion. Step 1 is finding that low-stress zone. Step 2 is maintaining a continuous line of reinforcement. But step 3 is where things go off the rails for a lot of people. You have to stagger multiple lap splices. Think about it. If you group all your laps into the exact same cross-sectional plane of a column, you've just built a massive, congested weak spot right across the entire grade. By staggering them, you maintain full continuous strength without creating a localized point of failure. Section 5. Pro tip: checking the drawings. This is the non-negotiable step. Listen, as a lead engineer, this is my final, non-negotiable piece of advice for every single supervisor, inspector, and student out there. You have to rigorously check your structural drawings and follow these ACI continuity requirements to the letter. The intent here is so incredibly clear. We are trying to prevent the disproportionate collapse of large portions of a structure after a localized failure. Proper lap splice placement gives a building the ability to redistribute internal forces. So if an abnormal loading event happens and one small piece fails, correct lapping means the building can still carry the load, even with huge plastic deformation demands. It's literally the difference between a single localized crack and a disproportionate catastrophic collapse. So I'm going to leave you with this question to ponder. Next time you step onto a construction site, will you look at a lap splice and just see two pieces of wire-tied steel? Or will you see the precise engineering, the calculated low-stress zones, and the exact line between safe yielding and total structural collapse? Because once you truly understand the physical why behind the code, the bending moments, the plastic hinges, the stress distributions, you hold the power to ensure that building stays standing when the earth decides to test it. Thanks so much for joining me on today's Explainer, and keep building safe.